Pluto's process through space constrains it to rise and fall in its circle as it converges with the ways of other divine bodies. This occurs especially when it crosses the direction of Neptune in the farthest locale of our nearby planetary group. Pluto, the charming and baffling dwarf planet, is generating extensive interest in the realm of astronomy. New discoveries show that Pluto may be on a potential impact course with Neptune, which is causing considerable uneasiness among cosmologists and space enthusiasts alike. Notable figures like Neil deGrasse Tyson and Michio Kaku have raised concerns about the possible repercussions of such a vast encounter. But what has driven Pluto to this potential collision with its neighboring planet? Moreover, what impact could such a celestial accident have on Earth? Join us as we delve into how Pluto's path intersects with Neptune's and why this orbital anomaly is troubling the scientific community. Initially classified as a planet, Pluto was later redefined as a dwarf planet due to its irregular orbit. However, despite this reclassification, Pluto continues to captivate the minds of astronomers and space lovers alike. Recently, experts such as Neil deGrasse Tyson and Michio Kaku have voiced concerns over Pluto's orbital path, which could bring it dangerously close to Neptune. This close alignment suggests that these two massive celestial bodies could interact in ways that may have significant implications for Earth. Pluto's orbit is unlike that of other planets in our solar system, elongated and unpredictable. Since its discovery in 1930, Pluto has not completed a single full revolution around the Sun, adding to its allure. Unlike the more circular orbits of the planets, Pluto's elliptical path stands out as a fundamental characteristic of our solar system structure. Another fascinating aspect of Pluto's orbit is its inclination, tilted about 17 degrees from the plane of the ecliptic, sharper than that of any of the major planets. This combination of a tilted and elongated orbit adds layers of complexity to Pluto's movement around the Sun. One particularly intriguing aspect of Pluto's trajectory is its periodic interaction with Neptune's orbit. For about 20 years in each cycle, Pluto's orbit brings it closer to the Sun than Neptune's, an astonishing event. Due to the otherwise distinct positions of the two planets, this phenomenon is striking. Notably, Pluto's orbit is not circular but rather shaped like an oval, causing significant fluctuations in its distance from the Sun. At its closest point, Pluto is around 30 astronomical units, AU, from the Sun, but at its farthest, it extends to more than 49 Australian dollars, twice Neptune's distance. Pluto's orbit is also tilted at a critical angle relative to the orbits of other major planets, further complicating its movements and interactions, particularly with Neptune. When Pluto and Neptune align in their orbits, their gravitational forces influence each other's paths. This intricate relationship highlights the interconnected nature of celestial bodies, with each exerting gravitational effects that shape the trajectories of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's motion with remarkable precision, offering a deeper understanding of its orbital mechanics and potential consequences for the stability of the outer solar system. Although a direct collision between Pluto and Neptune remains unlikely, the possibility still exists, fueling increased interest and concern among scientists. Despite its small size and distant location, Pluto continues to capture the attention of researchers and the public alike. But why hasn't Pluto collided with Neptune? The key lies in the gravitational interactions between the two bodies. When astronomers first studied Pluto's orbit, they were puzzled by its unpredictable behavior. Unlike most planets, which remain within a stable orbital plane, the ecliptic, Pluto's orbit deviates significantly, adding another layer of mystery. The real puzzle emerged when scientists realized that Pluto's orbit intersects Neptune's, yet despite this unusual overlap, Pluto's path remains stable. This phenomenon underscores the intricate mechanics of space and the difficulty of predicting celestial trajectories. Understanding the gravitational interplay between Pluto, Neptune, and the Sun presents a significant challenge for scientists. Predicting these interactions is akin to determining future positions based on initial conditions and gravitational forces. For Pluto, the interaction between its orbit, Neptune's orbit, and the Sun's gravitational pull creates a delicate system that keeps its trajectory stable. Terms like precession, libration, and VSOP variations help astronomers comprehend these complex dynamics. These concepts are crucial for ensuring the stability of planetary orbits. When Pluto crosses Neptune's orbit, it is still about 90 degrees away from Neptune, preventing any direct collisions. The process of libration ensures that Pluto remains safely in its orbit even as it approaches Neptune. VSOP variations, named after scientists like von Zeipel and Poincaré, explain why Pluto's orbit may seem erratic yet remains predictable over time. Although the universe may seem chaotic, the forces at play tend to stabilize planetary orbits, reducing the likelihood of a collision between Pluto and Neptune. This delicate balance highlights the sensitivity of celestial orbits to their initial conditions. Even small changes in a planet's velocity or position can cause significant alterations over time. Through advanced computational simulations, astronomers have modeled Pluto's orbital evolution, observing how minute variations in factors can dramatically change its trajectory. In the late 20th century, these simulations revealed that while Pluto's orbit may appear stable, it is still subject to chaotic fluctuations. Even tiny differences in Pluto's initial position or velocity can lead to substantial changes over time. However, Pluto's orbit has remained stable for billions of years, suggesting that despite its apparent irregularities, it follows a recognizable pattern. Predicting the behavior of planets with such unconventional orbits remains a challenging task, with the systems being so unpredictable that long-term forecasting is difficult. Simulations are useful for estimating potential outcomes, yet they also highlight the inherent unpredictability of celestial motions. Understanding Pluto's orbit is crucial, particularly when considering the slim possibility of a future collision with Neptune. Gaining deeper insight into these movements helps us understand the inner workings of our solar system and illustrates how even seemingly unstable orbits can be stabilized through gravitational forces. The way around the Sun serves as a great representation of space's idiosyncrasies. Unlike other planets, Pluto's orbit isn't perfectly circular. At times, it ventures closer to the Sun than Neptune does, adding to the intrigue of its cosmic dance. However, the chance of a collision between Pluto and Neptune is small. It is crucial to recognize the powerful forces at play in shaping their orbits. Gravity, the invisible force that governs the movement of celestial bodies, ensures that Pluto and Neptune remain in their designated paths despite their apparent potential for collision. The study of Pluto's orbit offers significant insights into the forces that govern space. What may initially seem chaotic is often the result of finely tuned gravitational interactions. Constant research and observation are essential for expanding our understanding of the solar system and beyond. The prospect of a Pluto-Neptune collision raises fascinating questions about the potential changes in our understanding of the outer solar system. Even though we have made significant progress in space exploration, such an event would highlight how much we still have to learn, signaling the need for further research. By investigating how larger planets influence Pluto's orbit, astronomers are uncovering crucial information about the behavior of the entire planetary system. This research reveals how the positioning and movements of planets can affect the trajectories of other celestial objects in space. Despite space's complexities, the possibility of Pluto colliding with Neptune continues to concern astronomers. This scenario raises the question: how could such a collision occur, even though it seems unlikely? Neil deGrasse Tyson, a prominent astrophysicist, has commented on Pluto's reclassification as a dwarf planet. He sees it as a major step forward in our understanding of the universe, reflecting our ongoing efforts to learn more about celestial movements. Tyson believes that events like Pluto's renaming engage the public in the pursuit of space science and emphasize how much remains undiscovered. Tyson, along with other experts, has raised concerns about the potential dangers of Pluto's orbit, particularly the risk of collision with Neptune. He suggests that such an impact would be a monumental event for our solar system, causing widespread disturbances throughout the universe. A Pluto-Neptune collision could release massive amounts of energy, potentially breaking Pluto apart and sending debris into space, possibly colliding with other celestial bodies. Even Neptune's orbit would be disrupted by such an event. Michio Kaku, a well-known theoretical physicist, offers his insights into the celestial mechanics at play. Kaku emphasizes that studying Pluto's orbit is crucial for understanding the future of space exploration. He believes that by comprehending the gravitational interactions between bodies like Pluto, we can improve future missions and navigate space more safely, minimizing potential risks. His work in string theory, a framework for understanding the fundamental laws of nature, could also reveal more about the forces shaping the universe. Kaku argues that studying Pluto's dynamics can unlock deeper insights into the forces that govern space and time itself. Both Tyson and Kaku agree that monitoring a potential Pluto-Neptune collision offers a unique opportunity to advance our understanding of the universe. Such an event could provide valuable data for string theory, which models the universe as a series of vibrating strings. Although the immediate effects of a Pluto-Neptune collision on Earth would be minimal due to the vast distance, the scientific benefits would be significant, enhancing our understanding of theoretical physics and the nature of the cosmos. As researchers continue studying the gravitational effects exerted by neighboring planets like Neptune, the ever-changing nature of space becomes increasingly evident. However, space remains full of mysteries. The three-body problem, where multiple celestial bodies exert gravitational forces on each other, is just one of many challenges astronomers are working to solve. Ongoing space exploration is vital for expanding our knowledge of the universe and the laws that govern it. While the probability of planetary collisions is very low, the possibility persists due to the influence of gravitational forces. These forces can subtly alter planetary orbits, potentially leading to collisions over time. One example of this phenomenon is the TRAPPIST-1 system, which contains 7 Earth-sized planets. The gravitational interactions between these planets can create orbital resonances, potentially destabilizing their orbits and leading to future collisions. Researchers are closely monitoring these systems to better understand how celestial bodies interact and how their paths can change. In addition to planetary interactions, rogue planets, celestial bodies that no longer orbit a star, can drift through interstellar space. These planets, once part of a solar system, can travel vast distances and occasionally collide with other star systems. However, the immense emptiness of space reduces the likelihood of direct collisions between rogue planets and other celestial bodies. Ultimately, when galaxies collide, the immense gravitational forces involved can disrupt the orbits of stars and planets. While planets themselves might not collide directly, their orbits can be altered, potentially ejecting them into space or causing them to crash into other planets or their host stars. Such disturbances can lead to the formation of new celestial bodies or even new stars. The late heavy bombardment hypothesis suggests that around 4 billion years ago, a surge of impacts from comets and asteroids occurred, possibly caused by the movements of outer planets like Jupiter and Saturn. These impacts reshaped the trajectories of smaller objects in space, many of which were ejected into the inner solar system, where they collided with Earth and other inner planets. Though these impacts did not involve direct planetary collisions, they played a significant role in shaping planetary surfaces and compositions. It is even believed that these collisions contributed to the delivery of essential elements such as water and organic molecules to Earth, creating the conditions necessary for life. These ancient impacts serve as a powerful reminder of how gravitational forces from larger celestial bodies can drastically alter the orbits and trajectories of smaller ones. Similarly, Pluto's erratic orbit raises questions about a future collision with Neptune, while past cosmic events highlight the dynamic and evolving nature of space. The delicate balance of gravitational forces governing planetary systems continues to be a central focus of research, helping us understand how our solar system, and the universe as a whole, has evolved and will continue to change over time. The potential for future encounters, whether between Pluto and Neptune or through other cosmic phenomena, underscores the complex interactions that drive the ever-changing nature of space.